Okay, welcome back. So in this video, we'll be examining the uh, second order differential equations. Okay, so in this context, we'll be looking at uh, linear second order differential equations. Okay, ODEs in this case, right? And then I'll get into uh, how the method of figuring out general solutions for solving second order differential equations is formulated by looking at an application using mass spring systems. Okay, so without further ado, let's get started. So let's look at the physics behind a mass spring system. So assuming that we have a spring that is moving in the horizontal direction, okay, moving in the x direction. So we'll have sort of a mass that's hooked on, and then there's some terminology for a spring. So they denote this as y, but you can use x for the horizontal direction. But equilibrium, this is basically where the displacement is zero, right? So equilibrium, that's that point where y is zero, okay? And then by Newton's second law, of motion, the force that is applied is equal to the mass times the acceleration. Okay, and we also know that acceleration is the second derivative of displacement. Okay, so if y denotes the displacement of the spring, where the mass is on the spring, okay, we can write out the force of the spring is equal to m times the second derivative of y with respect to t squared, right? With respect to t. So right here, this is Newton's second law, okay? Since we're dealing with a mass spring system, by Hooke's law, the force that is applied on a spring is proportional to the displacement. Okay, so K is what's called the spring constant. K is the spring constant. And it's minus K times Y because the force is acting against the motion of the spring. Okay, so if you're stretching the spring, there's a tendency in the spring to act against that pulling force, right? So as the spring moves this way, right, there will be a resulting force that's acting against the spring. So that's where minus ky is denoted as, right? Sometimes you might have a mass spring system that is inside of a tank, right? Um, of some other fluid, right? Air is a fluid, right? So um, uh, uh, there is some friction force that's acting against the spring, right? Um, uh, uh, but if you're moving along air, right? So if the mass is moving along towards air, there's very little damping force, right? But if you're in like a swimming pool, and if you are uh, uh, let me go back by saying, so if the mass is moving along some other fluid, you'll have what's called a damping force, right? So so you'll have this quantity, I'll say B times V. So B times V, V is the velocity of the spring. So this is what's called the damping. The damping force. So it's similar to like when you walk in a swimming pool, when you walk towards your friend, you'll see that the motion is it's slowing you down as you walk on the swimming pool towards the other end of the swimming pool or your friend, right? So it's the similar force that's acting against that spring, okay? And that's what causes the spring to slow down, okay? So altogether, you'll have this equation. So by Newton's second law, we have the mass times the acceleration, which is the second derivative of the position, right? And that is equal to minus k times y, all right? You'll have a damping force. And we know the velocity is the rate of change of displacement with respect to time. So we can write out this damping term as B times dx dy dt, dy dt. So dy dt, like this. And you'll also take into account some external forces. Okay. So you'll have some external forces that may act against the spring. So if the spring is on a magnetic field, well, we're going to have some external forces that are in account with the motion of the spring. Okay. But excuse me. So we can actually formulate the differential equation like this. So we'll have m times, I'm going to label d this quantity as y double prime of t. This quantity right here, this is minus b times y prime of t. And then this quantity is plus k times y of t. And this equals to some external force function, capital F. All right. So this right here, this is the second order linear differential equation with constant coefficients. M, B, and then K are constants. And this is the differential equation that locates the position of the mass on the spring. Okay, so this is plus here. So yeah, my double prime of t plus b times y prime of t plus k times y of t equals to some external force function. Okay. So there's going to be some terminology that I need to mention in second order differential equations. And I believe it comes up in the next slide. So, oh, actually, no, not yet. Actually, let me write it right now. So in this context, we're going to be looking at second order differential equations that are homogeneous or homogeneous. Okay, so let me erase this. Don't worry, we'll get to that soon. So, okay, that's good enough. So, homogeneous or homogeneous. So, you're going to deal with differential equations, second order differential equations that are homogeneous if this function of t is equal to 0. So essentially, you have a second order differential equation that equals to zero, right? So the right-hand side will always be zero. Okay. And uh, and then so the let me label out the constants again. So the m variable is mass. B is the damping coefficient. And then K is the spring constant, right? K is the spring constant. All right. So for example, if I have so in this equation, if we have B equals zero, so that means there's no damping. So this is a scenario where we have a no damping. Okay. And then this is a homogeneous equation. So the external forces are zero. Okay. So the equation they're referring to was the one I wrote out a few seconds ago. So y prime of t plus k times y of t is zero. Okay. So we'll look at that. We'll look at this general solution in a bit more detail. But I want you to try to verify that this is a general solution for an equation, a differential equation, where the constant is zero and it's homogeneous. So in this case, we'll have m times y double prime of t plus k times y of t equals to zero. All right, omega is so y of t. This is cosine of the square root of k over m times t. All right. This shouldn't take too long, but really, so you're using the chain rule. So y prime of t, well, this equals to the square root of k over m, or I should say minus the square root of k over m times sine of square root of k over m times t, and then y double prime of t. This is minus k over m times cosine of the square root of k over m times t, right? So if we plug this into the equation here, so we'll have m times y double prime of t, which is minus k over m times cosine of the square root of k over m times t, and then plus k times cosine of the square root of k over m times t. And this has to equal zero, right? And we have that, right? So it'll be minus, so this means we'll have minus k times cosine of the square root of k over m times t plus k times cosine of the square root of k over m times t is zero, right? So this function here, y of t equals to cosine of k square root of k over n times t, would be a valid solution for the differential equation that's indicated right here, right? So let me move over here so we can see that. Okay, so hopefully that made sense. So I'm going to go over the method of solving a linear second order differential equation with constant coefficients. This is a lot easier to solve. If you don't have constant coefficients, it's going to be much more difficult to solve. It will involve matrices, but anyway, we'll go over those soon. Okay, so I want to define a second order differential equation like this: a times y double prime of t plus b times y of t plus c times y of t is 0. So this is a second order linear ODE. And this is homogeneous. And this has constant coefficients. A, B, and then C, right? A, B, and C. So this is the second order linear homogeneous differential equation in standard form. This is in standard form, right? And so to figure out a general solution for this type of equation, all we're going to do first is write out a guess function, right? We're just going to guess. So far, the exponential function worked out pretty nice. So what if we have a general solution like this, right? A general solution may look like this, right? Y of t equals e to the rt. Well, if I differentiate this once, y prime of t, this will be r times e to the rt, and then y double prime of t equals to r squared e to the rt, right? Okay, so what that is going to look like. So if we plug in these functions into the differential equation right here, so by the differential equation, we'll have a times y double prime of t, which is r squared e to the rt, plus b times y prime of t, which is r times e to the rt, plus little c times e to the rt equals to 0, right? Equals to 0. We can factor out e to the rt on the left-hand side. So we'll have e to the rt times ar squared plus br plus c. That equals 0, right? E to the rt is never 0, so so we can divide both sides by e to the rt. That's never 0. Okay, so we'll have a times r squared plus br plus c equals 0. This is the key to solve what the general solutions for a second order differential equation would look like. So this is what's called the characteristic equation. Not to be confused with the characteristic equation in linear algebra that deals with eigenvalues and all that good stuff. All right, so let me get a larger eraser. So we're excuse me. So we're assuming that y of t looks like this function, right? E to the rt. Now there's going to be 3 cases, right? To what r equals to. And to solve for r, just use the quadratic formula, right? So r is equal to minus b plus or minus the square root of b squared minus 4ac over 2a, right? The quadratic formula that everyone knows and loves. All right, so and this quadratic formula here will give us the number of solutions and what type of solutions would look like, right? So the cases here that we want to examine is that so r is equal to some. So we're going to have 2 roots, right? R1 and R2. Okay. So the first case. So the first case is if R1 does not equal R2, they're distinct, and both R1 and R2 are real numbers. Okay, both R1 and R2 are real numbers. So in that case, we'll have two functions that are solutions, right? So one of them is e to the R1 times t, and the other solution, I'll label that as y2. Let me actually do it down here. So the other solution, y2, would equal to e raised to the R2 times t. Okay. And then I'm gonna mention this important fact in the next slide, I think. All right, in the next slide. If you have two separate solutions for a differential equation, then their sum is also a solution. So here's a fact to remember. So if y1 of t and y2 of t are solutions to the differential equation 1, then their sum, c1 times y1 of t plus c2 times y2 of t, is also a solution to the differential equation. Okay. All right. So, yeah, so their sum would also equal to, would also be a general solution, right? So in this form. So in that case, if you have a case where you have two distinct real numbers, the general solution would look like this. So C1 times y1 of t plus C2 times y2 of t. Okay. And I've also mentioned this before. If you have an nth order, so if you have a differential equation of order n, right, you should have n number of solutions. Okay. So that it has to deal with the existence and uniqueness theorem for figuring out solutions for ordinary differential equations, right? And so in particular, if you have two distinct real numbers, you should have two distinct solutions for a differential equation, a second order differential equation. Okay. So that's the case if you have two distinct real numbers for R. Okay. Also, we'll have a case where in the, let me erase this real quick. So we'll have a case in the quadratic formula here that we have two roots that are the same number, right? So we'll have another case if R1 equals to R2, right? If you have the same number, but it's yeah, you have two roots that are the same number. Okay. So this is going to be a little bit of a challenge because not only we want to have a set of solutions, right? We also want no commonality between those two set solutions. So we're going to have to add on this extra case where the set of solutions are independent. Okay. So they're not, so they're functions that are not generated by a scalar multiple of another, right? So, so for example, right, we'll have one set of solutions so if I call this R, R1, R2, so if I call this equal to R, I'll actually do that in the other slide. So, okay, so if we have R1 equals to R2, we'll call this number R. And so one solution will look like this. Okay. But we also want to construct a function that is also a solution to this equation here, right? So let's see. R times t. So what if I call y2 as t times e to the rt? Well, okay. So we want to show that t times e to the rt is a solution, right? That's the goal. We know this part, okay? All right. So we know that because, well, R satisfies the quadratic equation for the characteristic polynomial, right? So, okay, so let's test out to see if this is a solution, first of all. So y2 of t, right? This is t times e to the rt. Then y2 prime of t, we have to use the product rule. So this would equal to e to the rt plus t times re to the rt. And then y2 double prime of t. This would equal to r times e to the rt. And then we have to use the product rule again. So r times e to the rt plus t times r squared e to the rt, right? E to the rt. So okay. All right. So okay. All right. So now if you plug in this quantity, or I should say, yeah, here. So if I were to plug in this quantity, y2 prime of t and y2 double prime of t into the differential equation, I will get a times y double prime of t. So this would be 2r e to the rt. And then we'll have plus a t squared, t times r squared. Gotta be careful here. So t times r squared e to rt plus b times y2 prime of t, which is e to the rt plus t times r e to the rt plus c times t times e to the rt, and this equals to 0, right? Excuse me. So now what we need to do is gather all of the terms that don't have a t in front. So this term here and this term here. Okay, so we'll have so these constants will be two. Oh shoot. So it'd be 2 times AR R plus B times e to the RT. And then I want to gather all of the, oh, you can't see that. All of the terms that have a t in it here. So this is plus tr squared. Oh, Jesus Christ. Plus b times t. Oh, I'm sorry. This is a here. BT R e to the RT plus C times T times e to the RT. And that equals 0. Okay. So if I factor e to the RT, I will get 2 times AR plus B. And then if I factor out a T in the second quantity, I'll have AR squared plus BR plus C. And that equals 0, right? E to the RT is never 0, so we'll divide both sides by e to the RT. So we will get a polynomial in terms of t. So we'll have our constant, which is 2AR plus B, plus t times this quantity, right? Since we have a polynomial in t equals to 0, that means their coefficients have to equal 0. So what that means is, is okay. So we have 2AR plus B equals 0, and AR squared plus BR plus C equals 0. We know this is true since R is a solution for this quadratic equation, right? So this equals 0, and this also equals 0. So that's true. So what that means is y1 of t equals to e to the RT, and then y2 of t equals to t times e to the RT are solutions to the differential equation, right? Let's see, eraser. Oh, come on. Okay. So we know that y1 of t looks like this, and then y2 of t looks like this. Okay. And so the general solution will look like this. So y of t, well, it'll be c1 times y1 of t plus c2 times y2 of t. Right? If y1 of t is this, and then y2 of t equals to this function, right? So that's the case where we have a repeated root. Now a complex root. So we're going to have the final case where you have distinct complex roots. So R1 equals to R2, and they are and they are complex roots. So let's say R is equal to alpha plus beta times I, right? So a complex number looks like this, A plus BI, right? A is the real component, and then B is the imaginary component, right? If you want to learn more about complex numbers, I have a whole playlist on it. So, okay. So we know our guess function. So we know our, oh, Jesus. So we know that, so we know the guess function is equal to e to the RT, right? And so we're going to have, so we're going to have one function that looks like this, e raised to the alpha plus beta times I. And then we'll have another function, y2 of t equals to e raised to the alpha minus beta times I, right? So this is our set of solutions. That's what it looks like. And we also, if you are familiar with this, e raised to the ix, this should ring some bells here. In Calc 2, e to the ix, this equals to cosine of x plus I times sine x. This was Euler's identity, right? Right, Euler's identity, okay? So if you recall that in calculus, x can be any number, right? So, all right, so we can express y1 of t as e to the, I should say t here, forgot t, e to the alpha t times cosine of beta t plus I times sine of beta t. Okay, and then y2 of t is equal to e raised to the alpha times t times cosine of beta t minus I times sine of beta t. Cosine is even, so cosine of minus theta equals to cosine of theta, right? There's no sign change for cosine of theta, right? Okay, so this is a valid solution set, right? But we so we want to figure out a way to express our sum of solutions in a confined manner, right? So if we have two separate functions that are a solution to a differential equation, okay, then there's sum or they're multiple, right? There's sum c1 times y1t plus c2 times y2t is also a solution, right? So if I were to take the average of the two functions, right? For example, this is also a solution, right? So this would equal to, right? So I'll have e to the alpha t 2 times e to the alpha t times cosine beta t over 2. So this would equal to e to the alpha t times cosine of beta t. All right. So this is one function that is a solution for the second order differential equation, right? Like this. And also, if I were to subtract the two functions y1 and y2 and divide it by 2i, well, I'll just get 2i e to the, oh shoot, yeah, e to the alpha t cosine shoot, sine, I meant sine, the cosines go away, sine of beta t over 2i. This equals to e to the alpha t sine beta t, right? Okay, so this is also another excuse me, another function that satisfies the differential equation. Okay, so they label this function as your new y1 of t and this function as your new y2 of t. And so let me actually emphasize a little bit more clearly. Cosine of the capital y1 of t. This is sine. That's capital Y2 of t. Okay, so the solution, the general solution, right? right? So y of t is equals to C1 times capital Y1 of t plus C2 times capital Y2 of t. Okay, so that's a general solution for that case. All right, so hopefully you got that written down. It's recorded, by the way, so I'm going to erase all of this and go over some different terminologies that different terms about about what we're going to see in solving second order differential equations. So erase that and good. So I already mentioned this before. So if I zoom in here, so you can see it. So a pair of functions, y1 of t and y2 of t is said to be linearly independent, okay? So if and only if neither of them is a constant multiple of the other on all the interval I, okay? So this interval could be any real number or just a subset, right? A to B, okay? So we say that y1 and y2 are linearly independent on, we say that y1 and y2 are linearly dependent on I if one of them is a constant multiple of the other on all of the interval, all the values in that interval I. Okay. So to determine a pair of functions that is linearly independent, you'll use a quantity called the Wronskian. And I think it's coming up in the next animation here. So, oh, and this is just how to represent a solution for a general solution for a second order differential equation, right? So if we have y1 and y2 as any two solutions to the differential equation, ay double prime plus by prime plus cy equals 0, okay? Then there are unique constants C1 and C2 such that their sum satisfies the initial value problem. So the initial value problem that they are referring to is, well, this differential equation with constant coefficients that is homogeneous in this case. And you'll have initial conditions. Y prime of t0 is equal to w, let's say. So this right here is an example of an initial value problem if you're referring to second order differential equations. Okay. So, yeah, and then you'll have a sum of solutions being as a general solution for the differential equation ay double prime plus by prime plus cy equals 0. Okay. And the important fact here also is that y1 and y2 are linearly independent. So, and now we're going to define what the Wronskian is. So here's the Wronskian. So for any real numbers a and then b and c in the differential equation, right? So a times y double prime plus by prime plus cy equals 0. And if we have two set of solutions, y1 of t and y2 of t, as any two solutions to this differential equation, right? They are linearly independent. They are linearly dependent in this case. If this quantity y1 of tau times y2 prime of tau minus y1 prime of tau times y2 of tau equals to 0. And it holds for any point tau in on the real line in this case. Then it's what's called linearly dependent. And this quantity right here is what's called the Wronskian. If you had linear algebra before, the Wronskian, let me write this over here. So the Wronskian of y1 and y2 of t, this will be a function in t. This will equal to the determinant of y1 and y2, and then y1 prime and y2 prime, right? Just figure out the determinant of that function. The determinant of the functions of y1 and y2, right? So the Wronskian is just the determinant of this matrix, okay, which equals to y1 times y2 prime minus y1 prime times y2, okay? So, yeah, so with those out of the way, let's look at how we would, so let's look at examples on how we would solve for linear differential equations, second order linear differential equations. So here's an example. So solve following initial value problems. We have y double prime plus y equals 0. Okay. So we have this initial value problem, and I want you to try and solve it. Okay. But other than that, I'm going to go over the steps. So you want to focus first on the homogeneous differential equation, right? So we have y double prime plus y prime plus y equals to 0, right? So what we want to do is we want to associate y double prime and then y as the characteristic equation, right? In terms of R. So replace y with R, y prime, or I should say, so let me go back. So you want to replace y with 1, y prime with R, and then y double prime as R squared, and so on, right? So in this case, in terms of R, this equation would be R squared plus 1 equals to 0. I'm sorry, R squared plus R. R squared plus R. Okay. Oh, wait. Y squared plus Y prime. Excuse me. All right, let me start over. Okay. So I'm at Y prime here. So, yeah, okay. So try and solve this equation, but yeah, I wrote the example wrong. So if you solve the other one, great. But other than that, yeah, I'm going to solve this one here. So, okay, so R squared plus R equals to 0. And so this is the key here, to replace the y function and its derivatives with R, 1R, R squared, and all their respective powers on R, right? And from here, you want to solve for R. So if I factor out R on the left-hand side, I'll have R plus 1 equals 0. And so we'll have r equals 0 and then r equals -1. So we have two distinct real numbers as solutions for this characteristic equation. So our general solution, y of t, that would equal to, well, c1 times e to the 0t plus c2 times e to the -1t, right? And so y of t equals to c1 plus c2 e to the -t. Okay. So we know the initial conditions here. Y of 0 is 2, so that means y of 0 would equal to, in terms of the differential equation, we'll have c1 plus c2, and that equals to 2, right? So we have this set of this equation, and y prime of 0, so we have to take the derivative of this function, right? So that means y prime of t would equal to, well, c1 would be 0. So we'll have minus c2 e to the -t. So minus c2 e to the 0, which is 1, right? And that would equal to 1. So that means c2 equals to -1, right? So therefore, the particular solution would equal to so if c2 is -1, c1 is 3. Okay. And so c1 is 3, so that means, so y of t would equal to 3 times 3 plus, so it'd be 3 minus 1 e to the -t. Yeah, so that's the solution here. So 3 minus e to the -t. Yeah, so y of 0, that's 1, so 3 minus 1 is 2. And then y prime of 0, that's e to the -t, so that is 1. Great. So that is the general solution in that case, right? Yeah, so yeah. So with the other example, oh, Jesus Christ. Okay, can you work with me? I'll just go back with the other example. So with the other one, right, if I just deal with y double prime plus y, well, we're going to be dealing with sines and cosines in this case, right? So in that case, right, we'll have r squared plus 1 equals 0, which means that r squared is -1, so r is equal to plus or minus I, right? And so y of t is equal to c1 times cosine of t, right? Plus c2 times sine t, okay? So the alpha is 0, so e to the alpha t would be 1, right? So you'll have this solution set. And so y of 0, cosine of 0 is 1, sine of 0 is 0. So we'll have c1 and that equals 2, and then y prime of 0, this will equal to, so we'll have a negative c1 sine t, then plus c2 cosine t. So we'll have c2 equals to 1. So this general solution, this particular solution, so we have 2 cosine t plus sine t. Okay. So that's pretty straightforward. Let's do the next slide. All right, here's another one. Try and solve this initial value problem. Okay. So pause the video if you want to work on this for extra time, but otherwise, I'll just get right into it. So, really translate the differential equation into R's, right? So y corresponds to 1, y prime corresponds to R, and then y double prime corresponds to R squared, right? So in R, this differential equation would be R squared plus 2R plus 1 is 0, right? This is factored out as R plus 1 squared. So we're going to have a repeated root here of minus 1. Okay. So that means, right? So that means y of t is equal to C1 times e to the minus t plus C2 times t times e to the minus t. Okay. It's t time, baby. All right. So, we also know the initial conditions here. Y of 0 is equal to 1 and y prime of 0 is negative 3. So y of 0, what that means is our function is C1 plus C2 times 0. So we'll have C1 equals to 1, right? And then y prime of 0. So let me actually do this separate. Okay, I want to differentiate the function first. So y prime of t, that will be minus C1 e to the minus t plus C2 times e to the minus t minus t times e to the minus t, right? And then y prime of 0, so that would be minus C1 plus C2 e to the 0, that's 1, minus 0. So that equals negative 3. And so since C1 is 1, C2 is negative 2. So that means our particular solution, right? This would be equal to e to the minus t minus 2 times t e to the minus t, right? Okay. So, yeah, there you have it. Okay. So hopefully that works. Now, here's some comprehension problems for you to work with. This problem set has to do with the mass spring application problems. And this one just deals with second order ODEs that are homogeneous. Okay, so for next time, we're going to be looking at second order linear differential equations that are not homogeneous. So we'll look at differential equations of this type. Plus c times y equals to some function in t, right? And this will involve a little bit more strategy than just solving a homogeneous one, right? Homogeneous counterpart. So stay tuned for that. I hope you enjoyed this video. If you have questions, always let me know. Please leave a like and comment if you want me to make more of these videos. But anyway, I'll see you next time.